Hi, in this video, I'm looking at the Pythagorean identity and where it comes from and a couple of other identities that we get from it. So if we have a look at the unit circle, it's actually where we get our Pythagorean identity from. So if I just draw on any angle onto here and draw its value on, its angle on there, and I know that if I turn this into a right-angled triangle, then if I use sine theta being opposite over hypotenuse, that's going to give me the y value because we know that the hypotenuse has a length of 1. And the opposite value is the y coordinate of this point. So we know that y is our sine of our angle. And the same with that, the x is going to be our adjacent over hypotenuse. So x is given to us by the cos of the angle. So now if I take this triangle that I've just drawn, we've basically got a big hypotenuse of length 1. We've got this side here, which is y, which is sine theta. And we've got this side here, which is x, which is cos theta. And we can just keep the theta in there just because, but we don't actually need it for the rest of this. So if we look at this triangle and I apply Pythagoras' theorem to this. So we know that Pythagoras' theorem is the hypotenuse squared is one of the short side squareds plus the other short side squared. So we know our hypotenuse has a length of 1. So we have 1 squared equals one of the short side squared. So we could have, say, y squared. And then add on the length of our other short side, which is x squared. So now I've got 1 squared equals y squared plus x squared. Haven't done much, but if I go and replace my y with the sine, so I've got y squared here, so I've got sine of theta squared, and add on whatever the value of x is, which in this case is the cos of theta squared, then we will see that I'm starting to build up a relationship between cos and sine. Now, this is not the usual way to write sine squared and cos squared. This is sine all squared and cos all squared. We have a shorthand notation for writing this, which just gets rid of the brackets for us, makes it easier to look at. So sine squared is written sine squared of theta, and we have plus our cos squared, which is written very similar, cos squared of theta. And so that's our Pythagorean identity. Sine squared theta plus cos squared theta equals 1, because our hypotenuse was of length 1, and sine and cos give us the two short sides. And that's the basic standard Pythagorean identity, but from this identity we can get two others. So if I write my basic Pythagorean identity, cos squared theta plus sine squared theta equals 1, and I divide both sides by cos squared theta. So if I divide both sides by cos squared theta, so I've got to divide everything by cos squared of theta. I haven't changed it because all these cos squares will just cancel out because everything's been divided by cos squared. But if I look at what's changed, I've got cos squared over cos squared in my first term here. So that's just going to go to 1. And we've then got sine squared over cos squared theta. Now I'm going to write this as all squared. I'm going to factorize out that power of 2 and leave it as sine theta on cos theta. And then on our right hand side, I've got 1 over cos squared theta, which I'm actually going to do the same thing. I'm going to bring out that squared. So now I've got this, and the reason I've done this is there's not much we can do with the 1. But if I look at this term here, sine over cos, well, that's the definition of tan. So this is tan squared of theta. And over on the right-hand side, I've got 1 over cos theta, which is secant theta. And there's a squared there, so I've got secant squared theta. So this gives us our second Pythagorean identity, that 1 plus tan squared theta equals secant squared theta. So let's see if we can get the third one. There is one more that we can get out of this, and it comes from doing the same thing. So if I have a look again at cos squared theta plus sine squared theta equals 1. But this time, instead of dividing by cos squared, I'm going to divide by sine squared of the angle. So we're going to divide everything by sine squared of the angle. So now if I go through this, I've got in my first term, I've got cos of theta on sine of theta all squared, plus my second term is sine squared over sine squared, so that's just 1. And then on my right-hand side, I've got 1 over sine squared, so I'm going to have that as 1 over sine all squared. Now if I look at what I've got in my first term, I've got cos theta over sine theta. Now we saw before that tan was sine over cos, or we used before that tan was sine over cos. But now we've got cos over sine. So if I flip this fraction upside down, that means I have to flip this fraction upside down. So this is going to become 1 over tan all squared. We still have that plus 1 there. And on our right-hand side, I have 1 over sine, which is cosecant. So 1 over sine is cosecant of theta. So I'm going to have cosecant squared. And just fixing up this 1 over tan, well, that is cotangent. So I've got cotangent squared of theta plus 1 equals cosecant squared of theta. And so that gives us our third identity that is one of the Pythagorean identities. So if we use our definition that sine equals y and cos equals x, and put that into the right angle triangle and apply Pythagoras' theorem to it, then we get the base Pythagorean identity, which turns up quite a lot in mathematics. But if we divide by either cos squared or sine squared of theta and tidy up what we have, I can get 2 more trigonometric identities. 1 plus tan squared theta equals secant squared, and cotangent plus 1 is cosecant squared.